In this video, we are gonna talk about the regression diagnostics. In fact, we are gonna look at the like residual plots that we have, R square, like coefficient of determination. So we are gonna talk about we will talk about it a little. In chapter 2, we are going to go into the details. Still, we are in the review process. However, in all of these review parts that I'm telling you, I added like a little more equations as well that we're going to, the ones that we're going to use here. So let's go to the slides. Okay. So here, the most valuable regression diagnostic tool is the residual plus. If in examining residual plus, we are looking for trends or patterns. So look at here, for example, here is the raw residuals. So we have the residuals, and that's just an example. And versus something like this, the fuel consumption. And we will look at it. So you can't see any pattern here. And here as well, most of the time it's like this. Whenever we have a pattern on residual, like for example, if you have a linear relation in your residual represents error, right? So it's the same as error, in fact. So it means that you have some variables in your among your data, like in your experiments, that you didn't consider. It has a trend, so you can have that one as your variable. So because of that, when we are looking at the residual plots, let's say you have your regression model, you draw your regression models, and then you have your residual plots. If your residual plots has a pattern, it means that, oh, there is something wrong. So it's like that there was a variable that you didn't consider. So that's the main thing about the residual plots. It's like that. And when you want to draw it, it's very simple. You would have your residual, like E, that we had before. And then you would have you would choose it if you want to, like, for example, to have it like based on the, here is the data points fuel consumption, or here the data point was weight. So one of the data points you're gonna choose it, and then you would draw your residual versus on that, and you will see that if we have a trend or not. If we have a trend, it means that, oh, okay, so there is something wrong in your regression model, or it's your regression model is lacking for having like you didn't consider one of the variables. The next thing that in the analysis of the regressions and these ones we want to talk about is when we are talking about the residuals, provided the residuals are well behaved, another useful quantity to examine the regression model is the R square, or the coefficient of determination. Probably you have seen this R square 1,000 times. Whenever we have the scatter, and then like we would have a plot in the scatter plots on Excel, you will see that it's written like you would have the R square equal to something. So it shows the variability. It represents that how much variability of the model of the data our model is going to cover. And because right now we talked about the sum of the square of the regression and sum of the square of the total, it's very easy to find out the residual. So residual as well as the coefficient of the determination. So we would say R square is equal to SSR over SST. Instead of SSR, we can write down because SSR, sum of a square regression, is sum of a square of the total minus sum of a square of the error, right? So we can have like the R square regression, like coefficient of determination of our regression model, it's equal to the 1 minus sum of a square of error over sum of a square of total as well. So this ratio, R to above, or you can write it down by the you can get it from the correlation coefficient as well. So the correlation coefficient, we have another video on that. It's a small r, so you can square it. It's going to give you the same amount. Indicates what percentage of the variation present in the data is accounted for by the model. Like basically it's like this: the model that you gave me, how good it is to represent, like to present the amount of the variation of the real data. So R2 ranges from 0 to 1. In general, the closer it is to 1, the better the model explains the data. It is unwise to place too much emphasis on R square alone, or to consider it without examining residual plots. What I do all the time is that first look at your residual plots. If you are working, like, let's say you have in your project or your research, or like you have another course that you're working with, you want to work with these regression models like in the lab. So make sure that first look at the residual plots. Residual plot is going to help us a lot. After we make the regression model, then look at your R square. It is possible to have a low R square value with a model that fits the data reasonably well. And it's like that maybe all of the data points, it's a little like, it has all of them, they have deviation from the line, like the regression line, a little but deviation. So you would have your R square is low, but the model is a good one. It's a good representative of the real data. And I already told you the answer, but you can think about it. So under what circumstance might this happen? One is that I said that the deviation. Another situation, you can pause the video and think about it for a moment, and then come back and listen to the rest of it. So the answer is that we might have, like whenever we have nonlinear regression models, we might have a low R square, like coefficient of determination, but the model be a good representative of our like data points. So we are going to learn other things, and in the next chapter, on chapter 2, you will see that we're going to review that. But R square is one of the things that is going to be helpful for us, especially if it's like close to 1. But if it's low, we are going to try other things as well. Okay, so this is a very famous example. I thought that it's good that we would see the data. So we have 4 sets of data with the like 4 different colors I showed. And then it's very old, as you see, it's from 1973, the first time that they published it. And then the interesting thing about this data point is that when you're looking at the R square of them, all of them, they're the same. Like when we have the regression model for them, the R square for all of them is going to be the same. You can see the correlation factor for them is 0.82, 0.82, 0.8, 0.82. So it's like that if you want to square it, you are going to get the same coefficient of determination for all of these 4 models. And then when you're looking at it, like if this is X1, Y1, and for all of them, we have 11 observations. The mean for them, so it's like for X1, the means are, look at it, is for all of them is 9. And for Y is very similar as well. It's exactly almost the same. The only thing is that this one for data set number 2, Y mean for the Y is a little different. A standard deviation, so it's 3.16, 3.16, 3.16, 3.16. It's very interesting, right? And then for Y is 1.94, 1.94, 1.94, 1.94. So it's amazing when you look at it. Mean, standard deviation, and R is the same. So R square is the same as well. Now let's look at the data. So this is data set number 1. You can see the regression model, and you can see that how we can, like how our line is going to fit it. This is data set number 2. Number 3, so we have outlier that we need to consider, but we didn't. And number 4. So when you look at it, quickly you can say that definitely this is not a good fit, right? So this one, probably we need to remove the outlier, and then we are going to have another line regression, like linear line, that's going to make it a better fit. And then this one definitely is we need a nonlinear model, but we are using the linear one. This one, it might be a better one, depending on how far we could go to this. So when you compare it, even the R square is the same for all of them. The mean, a standard deviation, all of them, they were the same. But when you're looking at the data sets, it's like that. It's just that one of them, we can say that maybe the model is a good model for it. So that, I thought, it's a good example to look at it. So far we talked about the simple linear regression, right? And we are going to talk about these linear regressions on the next chapter, chapter 2. But just for one slide, I want to show you, just have it like a bridge. So let's talk about the multiple linear regression. So in reality, we have, most of the time, we have more than one independent variable. Like, for example, I'm interested to know the electricity load of this room. So I would say it depends, the electricity load of this room, it depends, it's going to be the function of the, like, let's say, temperature, outside temperature, because of, let's say, I have the thermal system that I have is electrical thermal system. It's like heating, for the heating space. So it's a temperature, outside temperature, the number of people that they're living in this room, like they're gonna, at this moment, number of pets that we have, or like the, what time of the day it is, like all of these ones are the variables. So we have more than one independent variable. So in reality, single linear regression won't help us that much. So we have to go to the multiple linear regression. Multiple linear regression is very similar to this single linear. The only thing is that for finding out the beta 0, beta 1, beta 2, like these coefficients, parameters, ANOVA table is exactly the same. Like the concept of the ANOVA table is the same. The overall significance of the model, do you remember I talked about that and I say that, okay, H null is that our intercepts, all of them, they're going to be equal to the 0. And H1 is that some of the beta, at least one of them, it's not equal to the 0. And that's the hypothesis testing for it. And then when we are, because we are working with the ANOVA table, we are going to have the F test, and the F test is going to be MSR over MSE, and then we are going to compare it with the F at the, like, from the table is P minus 1 and N minus P at the pre-selected confidence level. Like, it's like we would say 95% confidence interval. So alpha is going to be 5% when we want to go and read the F from the table. So when we are talking about the multiple linear regression, as I said, it's very similar to the simple linear regression. You can review chapter 12 of the CHE 220. It's already unlearned, or you can look at the summary file of it. If you want to, if you remember it, but you just need to review it like in 10 minutes, maybe the summary would be better. So it's like that. The only thing is that when we want to find out beta 0, beta 1, beta 2, with the same method of the least square method, we need to use matrix because we have more than like 2 variables, right? 2 parameters. When it was 2 parameters, we wouldn't need the matrix. It was like 2-dimension. We could simply solve it mathematically with the least square and getting the derivatives, like partial derivatives. But here, when we have beta 0 and beta 1, I would recommend that you would look at the matrix. However, we're going to talk about that in next chapter. Okay, so let's have the like see what we have covered in chapter 1. We talked about a lot about the estimation, like what's the inferences that we would have, a statistical inference like hypothesis testing and confidence interval, the regression model, linear one basically, and the ANOVA table. At the beginning, we talked about the normal probability plots, like the first part of the chapter 1, and then today talked about the residual plots as well. So you can, here is the concept map. In the next chapter, we are going to focus on the linear regression analysis more. So basically, it's going to be about the regression analysis that we are going to talk about it.